and I'm right in the throat of a volcano. Hey everybody, this is Garrett from Earth and Time, and today we're going to go check out the inside of a volcano here in Southern California, a volcano known as the Calavera Volcano in Carlsbad, California, on the north end of San Diego County. So let's go do a bit of exploring. Let's check out this park we're in, as well as check out the Calavera Volcano and talk a bit about its geology, and we get to see the inside of a volcano. How cool is that? Let's go take a look. I'm in the Calavera Preserve, which is a nice nature area within the town of Carlsbad, California. And what I want to show you all today, you can see on the other side here, there's this hill feature that sits on the other side of the Calavera Reservoir. Within the hill, you should be able to see some of these linear features, and those are called columnar joints, and those are very classic to volcanic features. And so what we're actually looking at here is the throat or the inside of a volcano, and we're going to go take a closer look at this. The Calavera volcano erupted somewhere between 13 and 18 million years ago, and I've seen estimates around 15 million years. So what was happening during this time? So during this time in Southern California, there were two plates coming together. There's the North American plate and the Pacific plate, and what ended up happening is you ended up with a transform fault here. Most people know the San Andreas fault, which creates a lot of the earthquakes here in Southern California. So this transform fault was setting up about that time. So this volcanism was probably related to the change in direction or the end of the subduction of the Pacific plate with the North American plate, and you end up with a series of these volcanoes. So the Calavera volcano we can see behind us is actually a dacitic volcano, which means it was a little bit more eruptive. So you can think of something more like a Mount St. Helens, maybe not quite that size, but something similar to that effect. And what we have exposed to us today here behind me is actually the neck of that volcano. So the big portion of the volcano that would have been up above us is eroded down, and now what we can see is basically what we call the throat of the volcano. And so it's really unusual and really neat to be able to see this portion of a volcano exposed, especially somewhere like Southern California, where we really don't think about volcanic features. Okay, so I mentioned that we're in a volcanic neck. So what does that actually mean? So if this is the profile of the volcano coming across here and it's erupting out of the caldera up here, so this would be the caldera, the little divot up here. The neck is the section that feeds the lava that explodes out, and that's actually what we're looking at here. So what has happened here is we've eroded a lot of this away. So now what we see, I grab my trusty pen here and we take it to the whiteboard, is I now have the surface of the earth doing something like this. So now I have the volcanic neck exposed at the surface. One thing I read that was interesting, there are some places here where you can still see some of the flow as well, and I took a quick hike around. I wasn't able to find those, but please comment down below. There are some areas where they said you can see some volcanic still down the sides that maybe would have been part of the older flank of this volcano. So pretty cool to see. But so what we're looking at here is this volcanic neck. With that in mind, we can see here's a nice sign that says it's a volcano, and this talks about this idea of Mount Calavera as this volcanic plug, or basically the throat or inside of the volcano. Now, why it's exposed here is because they were actually mining the material from here to build the dam for the Calavera Reservoir. So you'll see here it says columns of lava. These are known as columnar joints, and this is usually in the center of the volcano, and you'll actually see what happens is you end up with these six-sided hexagonal columns that develop here. Now there's places like the Devil's Post Pile that are popular or known for this, as well as some of the post piles outside of Mammoth, California. You can think of the Giant's Causeway in Northern Ireland as well that developed these. Now those are more basaltic in origin. These are actually dacitic, so they're a little bit more what we call felsic, or made up of slightly more silica and lighter materials than what we think of the basalt. So here is, from the city of Carlsbad, a little bit about Mount Calavera and a little bit about what geologists think about this volcano. So there's a couple layers here that already exist, And these are the Green Valley tronolite, which is about 100 million years old. So this would have been during the last part of the dinosaurs, known as the Cretaceous. And then there is the Santiago Formation that was deposited about 40 million years ago. And so the 100 million year old rocks would have been deposited when this area was starting to, there were a series of island arcs, and the Pacific plate was subducting underneath the North American plate, creating these batholithic type features and volcanic, intrusive volcanic features. And then much later, you'll see there's a huge time gap of 60 million years between these. So we have a pretty significant, what we call an unconformity between these two. And 40 million years ago, there were a series of oceans that came on top of here, and this is known as the Santiago Formation. And on top of that is a volcano that erupted here and built up here that's between 15 and 20 million years old. So you can go from 100 million years old to 40 million years old to 15 to 20 million years old. So this is a good spot to talk about the law of superposition. So what is the law of superposition? The law of superposition is one of the, if you will, rules, concepts, principles, laws that we follow in geology to help us understand and make observations and try to figure out what's younger and what's older. So here's a nice example of that. We have the 100 million year old rocks at the bottom, and then the next layer comes in on top of that. So that's 40 million years old. So you put this other layer, so we know the next layer's got to be younger than the first layer you put down, and eventually we end up with this 15 to 20 million year old volcanic feature on top, which is even younger still. So if we look up, going from 100 million, 40 million to 15 to 20 million years old. The other principle we can talk about here from geology, or law from geology, is the rule of cross-cutting relationships. So what does that mean? That means that whatever cuts across already existing units has to be younger than the units it cuts across. So what do I mean by that? So we have 100 million year old and then 40 million year old rocks, and what we know is that these are 15 to 20 million years old that are on top. So we talked about the law of superposition, but with the law of cross-cutting relationships, we know these had to exist before this volcanic material that we can see back here came through has to be younger than the stuff it's cutting across. So geology really is a lot of just making basic observations and using a lot of common sense. The stuff at the bottom is older than the stuff at the top. If there's something cutting through, it has to be younger than the things it's cutting. So there's some basic ideas that we can use in geology to help us understand and put relationships together between the different types of rocks. And speaking of different types of rocks, this is a pretty unique site, not only because you can see the inside of a volcano, but you can actually see all three types of rocks right next to one another. So if we look at the hillside behind me, we can talk about three different types of rocks right here, and I'm going to see if I can find a spot to get closer. But on the right hand side here, we have, I believe this is the Santiago Formation. So this is the 40 million year old formation on the right hand side, which is a sedimentary formation. So sediments are things deposited by the wind or sea. On the left hand side, we have the inside of this volcano, this Mount Calavera volcano, and these are those dacites or igneous rocks. Now, in between the two, where these igneous rocks came up, intruding and cross-cutting these sedimentary rocks, there's a slight zone of pink in here, if you can all see that, or a pinkish red, and those are actually metamorphic. So that's where the hot lava came along and actually cooked the sediments that were right here and created a metamorphic zone. So here it's really cool to see. It's almost like, I think of ice cream, a Neapolitan ice cream, right? Where you have your vanilla, your strawberry with the red in the middle, and then you have your volcanic, which is a little darker like the chocolate over on the left-hand side. So sedimentary, metamorphic, and igneous. So you have basically the triumvirate, or the trifecta, if you will, of geologic rock types all right next to each other. And that little distance there is probably, it's less than a meter, which is about 3 feet. So you say about a yard. So it's less than that in there, and you have all three types of rocks. So that's pretty unique and really cool to see at this Mount Calavera volcano. Okay, so we're going to head our way up and try to get closer to those columnar joints if I can. So we're going to see how the trail looks as I start working my way in that general direction. Now, as I'm walking here, I have now entered the inside of the volcano. So How come this is exposed again is because they're mining this rock to build the dam for the Calavera Reservoir. However, what I want you to point out is as I come around here, I am now inside this volcano. So you can imagine that this rim of this volcano would have come out here and come back around this way and reattach to the other side of this hill. And I'm actually in the neck, so the lower portion of this volcanic feature. And as I walk towards these columnar joints, which again are features you can see up in Mammoth, California, the Devil's Post Pile would be an example of these. You can climb on top of and look down. You can think of the Giant's Causeway in Northern Ireland. You can think of the Devil's Tower in South Dakota in the Black Hills as something similar to this. If you want to think about the internal part of a volcano where you can see that, if you can think of Arizona, you can think of something like Shiprock where you can see the internal part or the throat of a volcano as well. What's unique about this is one, it's dacite, which is a more felsic style of magmatism, which I don't think I've ever seen dacite columns before. Usually they're basaltic columns. And we're in, again, Southern California, which I've never thought of volcanoes, especially right off the coast of Southern California. The coast is a few miles in that direction here in Carlsbad, in the north part of San Diego. And to be inside this volcano like this is pretty spectacular. 13 to 20 million years ago, or as that sign said, 15 to 20 million years ago, I would have been not here. I would have been boiling, right? I would not exist because I would have been inside the heart or the throat of this volcano. So what I want to point out is all the stuff coming down along here. So this is all from those columns. One of the things I want to do is I want to get close to some of this debris coming down off these columns so you can see what the rocks look like. So we talk about crystal size in volcanic rocks, and we call them aphanitic if they're super fine grained and we can't see big minerals. Like this would be an aphanitic rock, right? This dacite. But if we say phaneritic if we can see bigger crystals, and a lot of times you can see that in things like granites where you see the big black specks, or the pieces of quartz or plagioclase or orthoclase in there. But this is very light colored and very fine grained. So this would be aphanitic. And again, this would be a dacite. As I'm working my way up this quite steep path, approaching some of the columnar joints, you can actually see one of the joints that fell down here. So they create a hexagonal pattern. This one's been eroded, so it's got a little bit more of a rough hexagonal pattern, but you can see the sides coming down, creating the columnar joint. And we'll get up closer to look at some of these. All right, now I've hiked up to the base of these columnar joints, and what you can see, especially with some of these ones on the bottom here, is you can see those hexagonal patterns associated with them, and you can see the columns that they develop. Pretty spectacular. So these are a result of slow cooling within the neck of the volcano. So I am standing quite literally in a volcano's throat right now. And you can see going off towards the north what it looks like. In that direction, the volcano is all gone. That way, it's been eroded or mined for material. But here, it exists right above me, and I'm right in the throat of a volcano. I worked my way up, and I'm now standing underneath these dacitic columnar joints. And we can look behind me and see where I came from and where I'm at now. And you can see me for scale. This is a big cliff face. Really cool to see. Let's go work our way up the trail and see what the top of this feature looks like, and see if we can see what these columnar joints look like from a bird's eye view. So now I'm on top of the dacitic flows and the columnar joints. I'm trying to see what they look like from up above. Here's my hand for scale. We can see this fabric coming through here, but I was trying to see if we could actually identify the columnar shapes anywhere in here. and they're not jumping out at me just yet. Let me look around a little bit more and see if we can see some of those pop out. Here's one. So we can see this side, this side, this side, and so we can counter all the way around and get about 6 sides around this feature. Now here's my foot for scale, so you can see what the size of these are. So they're about a foot, my foot across, size 11 shoes across there. So you can see what that looks like, a columnar joint from on top. But you'll see they get really weathered very rapidly. So water gets in between these cracks and wind starts moving the material as it erodes out. And so they quickly weather, and it's hard to see the columnar shape from on. Here I am on top of the volcano after we looked at that columnar joint. I just want to show you the view. Pretty spectacular view from up here. Pacific Ocean's right over there. I can actually see the ocean from here, from where I'm at, and I can pan around. There's a couple other people hiking up here today, and the wildflowers are out in full force. And what a beautiful view from up here. Have to be curious what those hills are out over there. I don't know much about that area. I'm learning about the geology as I'm walking around here with you all and trying to figure out this story and do a little bit of reading on the way. What I want to do is point out something here, and as a geoscientist, what we do is we try to look at what's happening out in front of us and look at what's happening in nature and come up with some stories. So based on observations and based on geologic principles. And one of the things I found that was really interesting as I'm standing up here is we have the volcano, and you can see the heart of the volcano here. If I look out towards the reservoir and you look where the dam's at, one of the things that's really interesting is you'll see there are these Cretaceous tronolites, the Green Valley tronolites are here that are about 100 million years old on the left hand side, and you can actually see them crop up on this hillside, on the next hillside, and they crop up going down this valley, crop out going down that valley. However, if we look on the right hand side, what we see is a lot of buff colored material, and this is the Santiago Formation. So if you remember, these are 100 million years old on this side, the Santiago is 40 million years old. To have two different age rocks next to each other requires something to happen. In this case, I believe what's happening is I think there is a fault cutting right through this area somewhere. So we have the Cretaceous on the left hand side, we have the Eocene, the Santiago Formation on the right hand side, which means there has to be a fault running through here. All right, all. So to better understand the fault that sits here, let's go to the trusty whiteboard. Here's my sketch of what's happening off in the distance. I tried to line up the fault roughly where I think it'd be at. So I'm standing on this volcano portion here, which we can see right off to my left, and it's below this cliff face in front of me. We have the reservoir right out there, and to the right, basically the dam, we have the Santiago Formation, which is about 40 million years old. That's the 40 million years ago, MYA, which is on this side, and on this side we have the Green Valley tronolite, which is about 100 million years ago, which is here on the left hand side. So the fault would run right about through there, about where the dam is, roughly, give or take a little bit. So this gives you an idea of what we're actually looking at here with my little trusted whiteboard. Now I've transported all the way from up there where I was talking about the fault zone, all the way down here where you can get a closer look at the Green Valley tronolite, this 100 million year old Cretaceous rock on this side. And if I turn to the right, you'll see none of that exists over here. In fact, what you can see is there's a couple of areas where you can see some buff color sediments over here, and that's all part of the Santiago Formation that's 100 million years old. So the question is, where does that fault run through here? And I believe maybe that fault runs kind of through this area where you see this little notch. And it's actually where the hiking trail is, and it goes towards where we see the volcano in the background, the Mount Calavera Volcano. So the fault could run through there, work its way all the way back around, Santiago Formation, Green Valley Formation on this side, and the fault runs somewhere right in this area. Pretty cool, and wanted to show just a different view of where that fault could be from where we started at. So now let's go transport back on top and learn a little bit more. So if we're going to take a cross-sectional view, so what do I mean by that? That means I'm going to take a slice of the earth, kind of about where the dam is. So it's not going to include the volcano, but I'll talk about where the volcano would be at in this. But if I was going to take a cross-sectional view, so I line up the fault in here somewhere and I look at what's on the left-hand side, of the dam, which is this Green Valley Formation, 100 million years old. And then on the right-hand side over here, the Santiago Formation, that's 40 million years old. I can show how this red line is a fault, and it's dropped the younger next to the older, which means the older dropped down even farther, right? So you can see the top of the, say, the Green Valley here. Although we know this is some kind of unconformity, there's erosion at the Earth's surface, so we're missing a bunch of time above that, right? That was 100 million years ago, and it's exposed today. And then on this other side, we can see where the Green Valley is in Santiago. So what does that tell me? So there's some things we can tell from this as a geology lesson, and that is the stuff on the left side probably had the Santiago on top of it, but it's all missing now and been eroded off. And I've drawn this as a normal fault. That's my guess of what kind of fault this is. So it's dropped down off to the east relative to the coastline out there to the west. So it's dropped down that way, which puts a Santiago over the Green Valley. And if we were going to put a volcano on, I would put the volcano at the top of the fault. So if I was going to take this cross section back a little farther through this area, I would suggest that the volcano was probably erupting because the fault was here. So you had magma at depth, the magma lava, right, is following up, and eventually you have this explosion of a volcano that's here. So that's kind of the story I see here as a geoscientist at Mount Calavera. I'm going to introduce you to another new geology term. So if you're hiking here at Mount Calavera, and I just came down the path, so the dam is out that way, instead of going towards the heart or the throat of the volcano, you turn right and come down. There's some outcrops along the pathway, and you're going to see these circular features, and these are called Lisengangen banding. So this is where iron-rich waters came through, and the iron was deposited, which gives it this color that you see here, this rust color, and it creates these spherical patterns that they call Lisengangen banding. Pretty neat to see that here. I worked my way back down, trying to find a spot where we can get up and put our hand on this metamorphic zone over here, and I wasn't able to find a spot to do that. So unfortunately, I'm not going to be able to get up close to this Neapolitan geology that's over here. But to remember, so you have the igneous, the metamorphic, and then on the other side, the sedimentary, which is really cool to see. If somebody knows a better spot to find this at, please share it in the comments down below. Would love to let other people know where they can see all through these rocks right next to each other. Okay, everybody, so we've taken a look at the inside of the volcano. We've taken a look at the top of the volcano. We talked about maybe why it's here. I appreciate you all joining me today. I hope you learned something. I know I learned a lot out here. It's so cool seeing this. I've never seen dacitic columnar joints before. It's really neat to go into the throat of the volcano and take a close-up look at that. It's neat to learn there's volcanoes here in Southern California. So with that being said, if you enjoyed this video, please give it a thumbs up. Please subscribe to this channel and hit that bell for notification to keep up on all my adventures on history and geology. I really enjoy having you all coming with me. Thank you and take care.